All right, today we're going to learn about some of the features and operations that we can do with the ternary phase diagram. All right, so this is a real-life ternary phase diagram of silicon dioxide, aluminum oxide, and iron oxide. So those are our end member compounds, as you can see, they're on each corner of the triangle. So this is a fairly complex diagram, and there's lots of information that we can get out of this diagram. So some of the information we can get is we can get what temperature a compound melts at or congruently melts at. So you'll notice next to the end member compounds, for example, SiO2, it says 1723. So that is the temperature at which silicon dioxide melts. And since it's a pure component, it melts congruently. Same thing for iron oxide down at the bottom, and also aluminum oxide at the bottom right. There is also some intermediate compounds. For example, the one right here in the middle also is represented by an open circle, just like the end member compounds. This indicates it's also a compound, a new compound, but in this case, an intermediate compound formed within this system. And so you'll notice a couple of them as you go out and look at the various regions of this diagrams. We also should realize that there are still the temperature contours that we can see: 19, 18, 1700 degrees. Again, that describes the liquidus temperature, and it describes the liquidus surface of the liquidus as a function of temperature, just like the topographic map that I compared to in last lecture. So in all of here, it kind of gives a reference guide for the different crystalline phases that you see throughout this material, because they refer to some by their crystallographic name, some of them by their oxide formula. And so we'll look at this, we'll kind of use this system as a prototypical system as we go throughout these lectures and talk about ternary phase diagrams. And so, don't be taken away by the vast information here. We'll sort of take it one step at a time and look at some various features on this diagram. All right, one of the first things I wanted to mention about the various features that we can get at, we've already done composition. Another thing that we've talked about in phase diagrams early on was solid solubility, right? The first system we looked at was an isomorphous system where there's complete solid solubility. So in the ternary system, the way that solid solubility manifests itself is by hatch marks. So in this case, I've blown up the bottom corner here, and you can barely see the sort of hatch marks here. But basically those hatch marks represent the extent of solid solubility. So for example, aluminum oxide in this system would be soluble up until the point where we see the hatch marks. That's what this is showing you. All right. Another thing that's going to be useful as we look through ternary phase diagrams is a concept of the primary phase field. This is the region over which a solid is first crystallized. And so what I mean by that is probably best represented in a binary system. So let's say we have this A-B system in binary phase diagram. And so our line here represents the liquidus, right? The point at which we first form a solid below. So the primary phase field just alludes to what is the solid that first forms. So for the region from 100% A all the way to this point P, the first thing that you form is alpha, right? In this whole region, over this whole compositional region, that alpha is the first thing that you would see as you decrease below the liquidus. From P to this eutectic point, the first thing that you would get is AB. right? That's what this primary phase field is. And then lastly, from the eutectic all the way up to 100% B, the first liquid that you would, or sorry, the first solid that you would form is beta, right? So those are our three primary phase fields in this diagram. So I show you in binary just so that you can kind of make the connection to ternary phase diagrams. So now let's look at what this looks like in a ternary phase diagram. So here I've got some various examples of ternary phase diagrams. So here, our primary phase field is going to be an area. Like I said early on, everything moves up in dimensionality by 1. So in the previous example, if I go back here, this was a line, this primary phase field. So now it's going to be an area. So in this example, this whole area that says alpha in it is the primary phase field for alpha. This whole area here, which is labeled AB, is the primary phase field for AB. Same thing for gamma and beta. So those are all the primary phase fields. Same thing, they're labeled down here, and same thing, they're labeled down here. So those areas are the areas that tell us the primary phase field for a particular material, and we should be able to identify what material that is. So this is going to have some uses as we go throughout these lectures and talk about ternary phase diagrams. Another thing to mention is that if we think about this primary phase field, what it tells us is that if we are at a temperature at or below the liquidus, that's the phase it's going to be, right? So if we're in this area, compositional area for alpha, and we're at or below the liquidus temperature, which we can identify the temperature by the temperature contours, right? This tells us the liquidus temperatures. Then we will know that our first solid would be alpha. Here, our first solid would be beta, and then gamma in this region. That's what it tells us. And so that liquidus is the equilibrium between alpha and liquid in this case. So when we have boundaries, so these boundaries between alpha and beta here, for example, what this arrow is pointing to, right? That is a boundary between these two primary phase fields. And so along that line, it means that alpha, beta, and liquid can be in equilibrium at the right temperature, given that it's right at the liquidus. All right, so one of the first things it can tell us about, and by it I mean the primary phase fields, is whether we have congruent melting or incongruent melting. All right, and so I again bring us back to this primary phase field shown in binary. So in these cases, if we look at alpha, which is the sort of terminal phase for A, so that has a composition down here. AB has a composition here, and B has a composition again at 100% here. So when we compare those compositions to the primary phase fields of those phases. So again, A has a composition here, and then the primary phase field for alpha is from 100% all the way to P. So the composition of alpha lies within its own primary phase field. It's within that range of compositions, right? And the same can be said for B and beta. But now if we look at AB, so AB has a composition here, but its primary phase field is from P to the eutectic, right? So this composition is not within the primary phase field of its own phase. And so that is an indication of incongruent melting. So congruent melting is when you have the composition within its own primary phase field, and then when you do not, that is incongruent melting. And so you can see this on ternary phase diagrams the same way. If the composition of a phase is within its own primary phase field, so let's look at this one down here. So for example, alpha, that's the phase of A. So it has composition here, so that's within its own primary phase field. But then if we look at AC, right? So AC has a primary phase field over here, but its composition, represented by this dot, is outside of that area, and so it's an incongruent melting material. So it lies in something else's primary phase field, right? So that makes sense. If you think about, we know that AC, that's the composition of it at room temperature. So if we have that composition and we heat it up, then we know at the very end, right? Then we're going to actually form liquid in this component gamma. So it's going to be different, and therefore it's not going to have the same composition, and therefore it's going to be by definition incongruent. So we can use these primary phase fields to determine congruent and incongruent melting. All right. So when we have the boundary of two solids and a liquid, on a binary system, that only happened when we either had a eutectic or paratectic or some other type of invariant point, like we have at these points highlighted. On a ternary, though, since everything goes up by 1, we, instead of having an invariant point when two solids and a liquid meet, now we can have two solids and a liquid meet at a line. And those are those boundaries between these primary phase fields, right? So between, for example, if we go to alpha here and beta, that line between them is the boundary, and we call that the boundary curve. So anywhere where we have two solids and a liquid at equilibrium, this is known as a boundary curve. So now, though, this is something we can't have in a binary system. We can't have 3 solids and a liquid at equilibrium at the same point, but we can in a ternary invariant point. So these can only happen at one specific point, and that's when boundary curves meet up. And so if we take another look at this section, so alpha and beta form the boundary curve between, we have another one over here, and we have another one over here. And they all meet up at a point E, labeled E in this case, and a point, there's another point over here labeled P, right? So we have 3 boundary curves meeting up at a specific point. And so these are ternary invariant points on the ternary phase diagram. So in this case, this is a ternary eutectic. You might have guessed it by the E. And then this one is ternary paratectic based on the P. So this ternary invariant point is the intersection of these 3 primary phase fields, 3 boundary curves. All right, so now I'm going to describe to you one way that we can actually determine whether we have a eutectic or a paratectic based on boundary curves. So if we so this is our projection, right? Our topographic map of the eutectic phase diagram. And so if you remember back to the 3D model, it looks something like this. And the eutectic point is one in which it has the lowest melting point. And so everything sort of funnels down to this one specific point in the middle. And so because of that, the boundary curves move down towards the eutectic and have temperature gradients down towards E. And so because all of those slopes of those different boundary curves, and you can sometimes represent those, or sometimes those will be represented by arrows on the diagram, then if you see this, if you see all of the boundary curves to a specific point flowing down towards a specific point, then that is by definition a eutectic point, a ternary eutectic. So in the other case, we're going to define anything that doesn't have that as a paratectic. So in this case, there might be two that go down, but one goes the opposite way, and any other combination of that. We're going to define those as paratectics.